All right, welcome to The Explainer. Today, we're going to dig into something really fundamental, the different ways statisticians think about randomness. And believe me, it might just change how you look at your next analysis.
Okay, let's dive right in with a big question, one that really gets to the heart of statistics. When you look at a sample of data, where does that randomness actually come from? I mean, is the world itself just random? Or did we inject the randomness by how we chose to look at it? It sounds kind of philosophical, but trust me, the answer has some huge practical consequences. So, here's how we're going to break it down. We'll start with the two main camps, the design-based view and the model-based view. Then, and this is the cool part, we'll see where they actually overlap in a really surprising way. And finally, we'll connect all of that back to the kind of textbook statistics most of us learned in school. Okay, first up is what we call the design-based view. The key idea here, the randomness comes from our actions. Think about things like survey sampling or official government statistics. This is their bread and butter. So picture this. You've got a big jar of marbles, and every single marble has a number written on it. In the design-based world, those numbers are set in stone. They are what they are. The only thing that's random is which marbles you happen to grab.
Okay, so this really gets to the core of it. The data values themselves, let's call them YI, are considered fixed. They're just numbers. The only random part of the equation are these things called selection indicators, or ZI. You can just think of that as a simple yes or no. Did we pick this item for our sample? And what's really powerful about this is that it's non-parametric. That's a fancy way of saying we don't have to assume anything about the data distribution. We don't care if it's a perfect L curve or something totally wacky. All right, now let's do a complete 180 and look at the model-based view. If you've done any machine learning or predictive modeling, this is going to sound way more familiar. In this world, randomness isn't something we do. It's just part of the fabric of the universe. So, in this view, you have to imagine some kind of data-generating machine out there in the universe. It's this theoretical process that's constantly creating data. The sample we actually get to see, it's just one possible outcome, one version of reality that the machine could have spit out. So going back to our marbles, the numbers on them aren't fixed anymore. Nope. They're the result of a random roll of the cosmic dice every time. And here is the absolute key. The data itself, each one of those YI values, is now a random variable. See? The randomness is baked into the world. It's not in what we did. But, and this is a big but, for this to be useful at all, we have to make some assumptions about that underlying process. We might assume that all the data points come from a source with the same average, or mean, and the same amount of spread, or variance. If we don't make those assumptions, we're just left with a meaningless jumble of random numbers. So this right here perfectly sums up the big split, right? On one side, you've got the design-based world, where the data's fixed, and we're the random part. On the other side, you have the model-based world, where the data itself is what's random. It's just one snapshot of what could have been. Now, you'd think that these two totally opposite ways of looking at the world would give you completely different answers, right? Well, this is where it gets really cool. Something kind of magical happens when the conditions are just right. It turns out, for what's called a simple random sample, and that's just when every single item has an equal shot at being picked, these two completely different philosophies, they lead you to the exact same formulas. The same way to estimate something and the same way to calculate how uncertain you are about it. It's wild. I mean, just look at that. Both of these frameworks, starting from completely opposite ideas about where randomness even comes from, they end up at the exact same equation for variance. That is such a powerful result. It's kind of like two physicists starting with totally different theories about the universe, but they both end up deriving the same equation for gravity. It tells you you're onto something real. Okay, so that formula they both agree on, it's the key. Because hidden inside of it is this one little term that, when you really look at it, unlocks our third major view of randomness. And this is the one that you probably saw in your intro stats class. Right, so this little piece right here, the 1 minus n over n part, that has a name. It's called the finite population correction factor. And it is the secret ingredient that connects all this to the kind of textbook statistics we all know. So what does this thing actually do? Well, it basically adjusts for the fact that when you're pulling from a small pool of items, every time you take one out, it changes the odds for the next pick. Makes sense, right? But what happens when your population, n, gets huge, like massive? Well, then your little sample, n, barely makes a dent. That fraction, n/n, gets super close to 0. And 1 minus basically 0 is 1. The whole term just kind of melts away.
And boom, welcome to our third view, the world of IID statistics. You've probably heard that term before. It stands for independent and identically distributed. It's the absolute foundation of most intro stats. And this framework basically pretends that correction factor isn't even there. And what does that mean? It means it's assuming you're sampling from an infinitely large population, where every single draw is a totally fresh, independent event. Okay, so let's pull all this together. We're going to put these 3 different ways of seeing the world side by side, so the differences are crystal clear. This table really is the big takeaway. You've got your design-based view, data is fixed, randomness comes from us picking a sample from a finite group. Then you have the model-based view, data is random, a product of some underlying process. And finally, the regular IID statistics we learn in school, well, that's really just a special case of the model-based view, where we assume the population is infinite, which is why that finite population correction factor just vanishes. Each of these frameworks is a different tool with different assumptions for a different kind of job. So why do we care about all this philosophical stuff? I mean, who cares where the randomness comes from? Well, it matters a ton. Because if you use the wrong framework, you can get the wrong answer. For example, say you're doing a political poll of 1,000 people in a small town. That's a finite population, right? If you use a standard statistical test that assumes the population is infinite, you might actually be overstating your uncertainty. Your margin of error might be bigger than it really is. So yeah, choosing your framework has real practical consequences.
So next time you come across a statistic, maybe in the news or at work, just pause for a second and ask yourself, is the randomness here in the world itself, or is it just in how we chose to look at it? Just thinking about that question will give you a way deeper understanding of the data that's all around us. Thanks so much for watching.